In this video, I want to give a second way to analyze what is the power function modeling a data set for the special case when you have very, very little data. Specifically when you have only two pieces of data, right, or 2 data points. So in the previous example we talked about for threesome, we had a chart and it had like 8 different pairs. So that's great. The problem is, what happens if I have a program that's really slow? Maybe it takes me a long time to generate those pairs of data, right? The problem size paired with how long it takes. And I want to avoid, basically spending all that time. I want to do my regression in as few pieces of, with a small data set as I possibly can, right? So what could I do? So it's actually going to be possible for us to do this kind of regression process, right, and figure out a polynomial from just two pairs of data. Which may be, if you think back to basic algebra, is a little bit iffy, because if you only have 2 points, generally what happens is you have to end up with something that looks like a line, right? Well, we can actually do a little bit better than that, though, by using an additional assumption by how the data set size changes. So let's take a look at what that is. So we're going to stick with the assumption that our t of n, right, is basically a power function, right? The function that predicts how much time my program takes to run a given input is a power function. And so the equation for it looks something like this. Okay, so that shouldn't be too surprising there, right? There's an assumption, right, that it looks like nested loops, but that's fine. It's very typical. And then we're going to do some algebra here. And it's worked out on the slide. So basically, you can imagine we have maybe our benchmark results on a size n input and then a size 2n input. And you can imagine we have those 2 expressions. Well, then given that we have those 2 expressions, we could divide them. That's what this first part here is doing, right? So we have kind of 2 valid expressions that relate t of n to n, right? One for basically normal size n and then one for 2 times size n. And we just divide them, right? So that's all legit there, and that gives us this expression here. And then I'm going to basically carry through the algebra, and then we'll talk about the result here at the end. So if we have the algebra, right, you can imagine we do some cancellations here, right? Cancel A, B, right, gets distributed. So I can basically just cancel that out on n over here, right? N over here. Then I'm basically just left with that right-hand side being 2 to the b. So I jump down to my next step. I have t of 2n over t of n equal 2 to the b. Okay, so things cleaned up a lot. Then I can imagine taking logs of both sides, maybe to rearrange it a little bit more. Gets me this over here. Log of t of 2n over t of n equal b. Little note here, whenever I draw this LG, what that is meaning is that I'm doing a log in base 2. Right, so this is log base 2 of something. All right, just a little FYI for the notation. So basically what this is saying is the following. I can recover b, right, that power in my assumed t of n, by taking the log of t of 2n divided by t of n. The key there, I only am touching 2 pieces of data, right? I need to know the run times for the data set, for the program on a data set of size n, and then the data set, and then the runtime on a data set of size 2n. So I don't need 6 or 7 or 8 different pieces of data, right, to feed the regression program in order to figure out, what is the function, right, linear, quadratic, whatever that fits this data. Given that I just have 2 pairs of data, right, and they are appropriately scaled, right? So one is basically a size n, the other one is a size 2n. Well, extra assumption, right, that assumption that one is double the size of the other means that I can algebraically basically write an expression for b in terms of those 2 pieces of data. So this is basically a lot nicer to work with, right? Because we don't need as much information about the program. We don't need to run it as many times. We just need to run it twice, and then we can figure out what that power is. So on the right, I have the chart that has our program size, our problem size, and then the times. And then the results are trying to do this sort of analysis on that data. So n and t of n should be familiar. The first new column here is called ratio. And ratio is being computed as a division of basically the t of n column. So this 8 over here is being computed by this 0.1 and 0.8, right? So divide them out, ratio of that is 8. That doesn't really mean anything. In the picture over here, our ratio is going to be that t of 2n over t of n, right? So this stuff over here ties to this column. Then I have there on the right-hand side, right, my other column there is log of ratio, right, which is just the log, the base 2 log of it. So the base 2 log of 8 is 3. So that is basically my entire function, my entire left-hand side of this expression, right, ends up being this column over here. So really that's going to be my b value, or the power in that assumed function, right, that models our running time. So it gives me the b over here, right, in this thing, right, the b is over here. Gives me that. So there you have it. If you have two pairs of data, you can still manage to recover a polynomial from it. And if you want to, right, you can solve for a as well, although there may be a little bit of inaccuracy there. As a quick question, if we were wrong about our assumption that our program can be modeled by a polynomial, how will that show up in the table? Well, basically that last line there, right, that log of ratio, will vary. So here you notice it's always the same, it's always 3, 3, 3. Basically represent that if I have a larger data set, right, I'm checking that ratio a couple times, well, every time I check it, right, it should basically have the same power there, right? The power on the function that models the running time for this program shouldn't change, right? It should stay the same. So if it started to vary there, right, we have 3, 4, 5, then we have an issue. Here it's all the same, so that means that we are correct in assuming that a power function models this data set.